Hello, welcome to the today class. Today we'll talk about deep neural net, also there are some of the related features. At the end of this class, I hope that you can understand you can actually understand some of the main components of the deep neural net. So in this class, I'm not going to give you I'm not going to aim for giving you the in-depth knowledge on the topic, since basically as a prerequisite of this course, I assume you know some of the low-level details about this deep learning. Instead, I'd like to give you the quick review on the topic. So since actually follow on the lecture material will be built on top of those some of high levels of deep learning. Also, at the last time we talked about the shift. So along describing shift, we talked about the automatic skill selection method. Also, we talked about LOG, DOG. DOG is the difference of Gaussian, which is approximation of the LOG. And also, we talked about some more low-level details about the shift as a local descriptor. So also, as usual, also I invited one of these our fellow students in this class, so that actually I'll try to have some interaction with him. Also, I went over some of your questions. Actually, I brought one question which is interesting to me. So he actually thought about it. Initially, he thought that this image retrieval is kind of the subtopic of the computer vision. But actually, he also once he took some of the lecture and he thought about the topic and the relationship between computer vision and this one. And then he actually realized that this image retrieval actually also utilize some of the components of the computer vision. Also, you can also talk about some other materials that may not be in the computer vision. So actually, this question actually brought up what are the main topics of the image retrieval in the relationship with computer vision. So since actually we are looking into content-based image retrieval, right? So along that line, we need to know we need to understand image. Along that line, we need to use a lot of the computer vision technology. But not just computer vision. In the end, we need to identify the related, or in other words, similar image from the database. And database could include the billions of images that are available at the web, right? So that process of the image retrieval should be done in an efficient way. So basically, it's about the retrieval or the search. You can think about Google search, right? So this topic actually they're looking into the intersection of the computer vision technology, also the search techniques. So so far I talked about computer vision, also talked about some of the feature techniques that develop in the computer vision. But later on, I also talk about some of the indexing scheme that also developed in the database, also this information retrieval field. So also that's one of the reasons why I talked about many of these related conferences. I talked about the computer vision conferences like CVPR, also machine learning. Also there could be this dedicated conference for this image retrieval, like the ICM or something like that. So there could be the main related the field of topics. So I wish that you can think about it, some of the novel angle to improve this image retrieval. Also, you can also adopt some of components of image retrieval to improve the computer vision or some other related these topics. So they could be so basically there's no predefined relationship between computer vision and image retrieval. I wish that you can find some novel relationship along that line. So that actually you can gain some interesting observation and new information along that line. That's the kind of my response to these questions. So there's no particular answer to them. I mean, no formal answer, no good answer. There could be I think that we will study more along that line actually. Thank you for bringing up that interesting question. So now I'd like to move on to the browsing the main components of deep learning. So here, I'd like to give this high-level message. So the deep neural net, nothing but provide a kind of a low-level and high-level feature. Before we talked about Harris corner detector, right? Basically, the Harris corner detector identified the interesting key point. So at that time, we defined the interesting key point as a corner, right? Also, last time we talked about shift. Shift also they're built on top of some of these LOG and DOG concept. Also, they used some of the blob detector it actually the thought that blob could be the kind of interesting the feature, right? Those are the kind of the low level actually information. But depending on your task, suppose that you wanted to identify this cat or dog, right? For that kind of high level task, to differentiate the cat and dog, we need to identify their kind of eye and some of the ear, something like that, right? Not just the edge or the blob, right? We need to develop, we need to be able to detect the more higher level concepts like the detecting eye and the color of the fur or something like that, right? So there could be the depending on your the task, there could be the more high level features on top of this kind of low level features like the edge or the blobs, right? So ideally, we need to have this kind of the different levels of the features. But in a way, deep learning provides this low level, high level feature in a very simple way. So that's why actually a lot of the features derived from deep learning used a lot for the image search. So that's one of the main direction that we will cover in this lecture. Also, the deep learning actually they achieved a lot of the very promising results across the many computer vision of the machine learning. Here actually some of you may see this kind of the deep learning architecture, which is actually AlexNet that proposed a long time ago. But actually some of the recent the deep learning for the computer vision task is much more complicated. But here actually we'll just talk about what are the main components of those deep learning. And probably next time I will connect the deep learning into the computer vision task. So also there are actually the deep learning actually it's under heavy investigation right now. I mean every month we are getting the new paper about the new architecture, new components of the deep learning. So it's almost impossible to cover those recent the deep learning technology within this lecture. But actually I'd like to point out that there are actually many features and codes are available actually. So actually, AlexNet, this architecture, also available at the cafe. Also there are many advanced techniques like the very deep convolutional networks, which actually using up to 17 layers. I'm not going to talk about the detailed one here, but this AlexNet has actually different layers. You can treat that this actually a separate independent layer. But it doesn't have the many layers. It has only the 6 or 7 that kind of layer. But the very deep convolutional network is that it actually it has a much more layer, like up to 19 layers. So here convolution. I will talk about this concept of convolutional network later on. But here you can treat that it's just some different types of another version of the deep neural net. Also, about 4 years ago, there's actually deep residual learning, which shows actually much better result of this very deep network, but it actually has a much more different layers actually. So you can certain the residual learning to enable the deep neural net to achieve the more layer, so that we can gain the better accuracy. So you can see that this actually some of the illustrations. The schematic architecture of this residual learning, you can see that there are a lot of the layers. But again, still, there are a lot of the recent technology along this line. So you can actually check out this homepage, and you can see some of the related actually the techniques. But actually, these are actually different deep learning architecture, but they're actually you can see that actually it also comes with a different weights. Here the weights could be interpreted as some sort of the feature that we can use, that we can treat like the health corner, the feature point, or the fifth feature, something like that. I will get back to the issue later on. Also this deep neural net actually performing end-to-end optimization with a lot of the training data. So before actually we actually had this very separated actually components. Like for example, we can manually define the feature like health corner detector, and then once we extract the feature, then sometimes we wanted to classify whether this image contains the cat or dog, right? Then we need to design separate this classifier using this SVM, something like that kind of this different classifier. and then we can actually, it actually has a kind of a separate independent layer of the extracting feature and you adopting classifier and so on. But the deep learning actually actually concatenate everything in a different layers, and then we can actually optimize in an end-to-end way. So I will get back I'll get back to that issue later on. Also, the deep learning can access if we can provide a lot of training data, we can achieve the very good accuracy. That's the one of key one. So in other words, the deep learning actually their aims not only not only having the good feature, but they're trying they're achieving the very good accuracy of their any task. Like in this case, let's say classification task in an end-to-end way. And then actually we can also adopt this approach even for the image search. So we can also we can design the feature in a way that we can improve the accuracy of image search technique. Also we can consider those extracting feature and image search task in an end-to-end way. So probably later on we'll talk about those with some of recent techniques along that one. So that's actually very different from the manually created descriptor. As I mentioned before, this actually we manually created every component, right? For example, at the fifth case, we actually manually created what are actually the layers of extracting the DOG, and then how we can detect this local maximum, and then given the local maximum, how we can actually extract the descriptor and so on, right? But here, all those processes actually they're encoded in the different layer, and then we optimize in a way that to achieve the best accuracy given this specific task. So those are the high-level methods. Now I'd like to talk about some of the deep learning techniques, the basic deep learning techniques, and then I will connect some of deep learning with the computer vision, with the image search. That's actually main theme of our course. Any questions so far?
I have some question of is the deep learning architecture there are max proving and strike and dance.
Yes.
But I don't know the concept of some words.
Yes. Some word. Here, yeah. So basically, there are a lot of there are some of the here. I didn't really explain this one. So I think that we will get back to that issue later on. So when we talked about convolutional neural net, this actually I'm just showing that this one of the example of convolutional neural net, but we didn't even talk about convolutional neural net. So basically, the max pooling is the kind of it's kind of the last time when we talked about the shift, we talked about actually identifying the local maximum, right? You can treat that the max pooling is kind of identifying the max response given that region. So you will see later on some of the convolutional neural net also related to actually some of the manually created the descriptor like a shift. So that so I hope that I can actually connect from the manually created one into deep learning along this convolutional neural net. But right now, actually, we are not going to talk about the convolutional neural net, but more low-level one, the deep, this kind of the basic deep neural net approach. Okay, so ideally, so here for the deep learning, basically the deep learning is nothing but some of the recent technology of the machine learning, right? Machine learning in general, what do we want to do there, right? There could be many different machine learning tasks. One is the object recognition. Given the image, we want to recognize a certain character here, the cat in this case, or sometimes we want to detect a certain region, right? Sometimes we want to segment particular region, right? So those are some of the actually machine learning tasks, and then also we can utilize this kind of the different machine learning tasks and combine them into image search, and then in a way that we can improve their image search, right? In a way that to identify the relevant image in an efficient way to the user, right? Those are in general here. Given this image, we wanted to predict also identify the complex high-level patterns, right? There could be the many different patterns, right? But they're not just the low level, the feature like the corner or the block patterns. Overall, actually, as I mentioned before, usually in the machine learning, we typically use the hand design feature. So given this image, we want to extract feature. So along that line, we design health corner detector or the SIF, something like that. Once we apply some of the machine learning algorithm like this classifier, the SVM or some other tools. Here, the extracting feature, we used a lot of the prior knowledge, right? When you talked about the SIFT, we actually utilize a lot of the information that we actually design that we derive from the image processing, something like that. But in the deep learning, actually, we wanted to optimize these two separate components in an end-to-end way. So actually, also for the feature, in terms of feature, there could be very low-level features like detecting the corner, right? Also, there could be high-level features like detecting the eye or this fur and ear, something like that, right? So depending on the level of the abstraction, there could be different levels of the features, right? So why just using the one low-level feature? Why just using the high-level feature? We can actually extract the varying level of features like the low level, middle level, high level, something like that, right? Also, we can also think about it this classifier in a way that we can also optimize to extract the feature in a way that to improve accuracy of classifier. Also we can design the classifier in a way that achieve the good accuracy given these extracted features, right? So actually in a way that actually we abstract the presentation and then we jointly optimize the extracting feature and learning the classifier within this framework of this deep learning. So along the line we use the multiple layers of features. Also, given that this multiple layer, we want to extract or discover useful representation. That's the main goal that we want to achieve here. So why deep learning? As I mentioned before, if we look at actually fifth, there could be the many different layers, right? The low level, the original image, we actually design a series of this LOG, something like that, right? So actually that in a way that each image actually serve as some sort of layer, right? Also, some of recent techniques scale well with some of a lot of data, and then by using the recent actual computing technology, we can actually achieve the good accuracy utilizing those many layers of a lot of data. So because of that, we are now able to use a lot of deep layers. But those techniques also very relevant in the prior machine learning techniques, right? Also, the neural net technique is not the really novel one, but why now actually deep learning technique is now can works very well and shown to achieve a very good result. There are some of recent change. One is that actually we are now getting very fast computers using the recent GPU. Also as you can see, cell phone comes with a very good the camera, so we can capture a lot of data. There could be a lot of the sensor data, and then sensor equipped devices, so that we can collect the data much easily than before. Also, there's a lot of the machine learning, deep learning, improvement in terms of the optimizer and some of the low-level details along the deep learning. Also, there are actually a lot of engineering work, so that we know that which technique works and which technique does not work, something like that. In a way, that actually deep learning also there are a lot of theoretical background, but actually it's kind of engineering effort. So basically, we collected a lot of information. In what configuration we can actually achieve the very good result with the deep learning. So those are the actual advances, recent advances. Because of that, we are getting very successful the result here and there. So as you can see, now we can actually achieve very good image recognitions and in speech recognition, a lot of the different on the task of computer vision or some other natural language processing and many other actual domains. now I just talk about some of the basic machine learning techniques, and then I will build on top of them to the deep learning. So overall, we'll start with this supervised learning. Supervised learning. Here actually we have the data training example. X is you can treat that this image, and Y could be the label. Let's say given this image, we can say that this cat or dog, something like that, is label. And then here, and then X is the vector of the image intensity here. Also the overall image actually considered as just nothing but a set of a vector of this value, right? And Y, immediately Y is actually the object class ID corresponding to cat or something like that. And then we wanted to learn predict function f of x that map from the x to this label. We wanted to actually the function f that predict very well even under this test data. And there could be many different actually classifier. But commonly we use this logistic regression. Logistic regression actually has a shape of something like this. You can say that x is actually you can say the input pixel value, and the theta is some of the parameter. And that is the logistic regressions looks like this. It actually has a shape of this, and then also the theta is kind of adjusting some sort of the parameter. Then we can control the shape of this one. So basically you can treat that this actual probability. You can interpret this function such that the fx actually give us the probability that given this each label becomes the one, something like that. So in the case, suppose that we want to identify here's if the y equal to 1, we can treat the cat, right? So basically this is nothing but this fx showing the probability that the input image having contain this cat. You can see that the probability going the higher as we actually have approaching the value along this feature. We can treat this actually some of the feature, some pixel value, something like that. And the question is that we want to actually identify the theta value, minimize certain objective function, right? Objective function. This is known as loss function, penalty function, something like that. And then this is very well known. This function for the logistic regression. It looks very complicated, but here its main idea is something like this. Here, suppose that given this the image, the true image, some of the image that contain the cat, let's say this training image, we supervise the deep learning. Basically, we supervise this logistic regression in a way that we give the input image with its label, the correct label, the cat, right? And at that case, we know it's cat, right? But at that case, we should learn the theta value in a way that the probable f function should be the 1, right? But somehow initially we may not get the exact probability of the 1, right? We may get some of the low probability, something like that, right? Then we need to teach the machine learning in a way that that's not good. You should update the theta value in a way that at the true cases you should return the probability of 1, something like that, right? So to do that, we need to provide some sort of cost, some sort of the penalty, some sort of the loss function. So that's why we actually have this kind of at that case this function actually corresponding to the shape over here, it's actually cost. It's nothing but at that case in this case the ground truth label is 1. Then if we actually showing the probability of the 1 here, it's correct, right? So we don't give any penalty. Okay, it looks good. We don't change it. That's the meaning of here. But as we approaching to our predict label coming to open to the 0, then obviously we are getting more incorrect the probability, right? So that's why we should give the more higher actually the cost, right? But along that case, we can actually we can take the log of this f function. Then actually we can actually have this shape, and then actually the same logic applied to the other cases. So if the image does not contain the cat, then at the case ID the probability should be 0, and then probably you should have this reverted cost, something like that. But anyway, I'm not going to talk about all the low-level details. It's a very well-known the logistic regression, the loss function for the logistic regression, also known as this cross entropy. Okay, then how do we turn the setup to minimize this loss function? So basically, we want to minimize the cost, right? In other words, we want to minimize the probability of getting the incorrect the prediction, right? So we actually typically we use this gradient descent. So its main idea is that suppose that actually this actually your loss function and this is theta. If we are here, we wanted to actually update the theta value from here to there, right? To do that, we need to compute the gradient here, and then if we take the negative gradient along that one, if we update the theta value along the here, we can actually get to this actually the local minimum here. That's the main idea. That's why we are computing the gradient. I'm not going to talk about the lower details, but the gradient looks like this. Further, given this our formula is logistic regression. You can see that this label our prediction is our error, and about this x value. We monitor that gradient, but we need to follow the gradient, the negative gradient along the downhill, right? That's why we take this minus to this gradient, and there's some sort of constant is actually also known as this learning rate. So we know that this is incorrect and how much step we have to take, right? That's actually that's the one. And then typically we use the stochastic gradient descent. It's nothing but we take a step from the gradient from the only small batch of examples. So given the training data set, we actually get the sum of sample of the training data set, small set, 16 examples, something like that. And based on that, actually we computed this gradient. So that's why it had the name of this SGD, stochastic gradient descent. And then it turns out that actually surprisingly it worked quite well even for the deep learning actually. So a lot of cases, a lot of optimizers actually you can see that we are using this SGD, something like that. But this gradient descent is a very common concept for the optimization actually. So so before we having the deep learning, we actually designed very different techniques to extracting the feature for the different actually task. I mean, some of the examples received, right? Now we will talk about how we can actually utilize this concept to extract this feature. Any questions so far? Okay, thank you. Now, based on this very simple logistic regression, we will actually the deep learning. You can treat the deep learning nothing but we just stacking this logistic regression layer by layer actually. So before we didn't really think about it actually the feature, but now we can think about we actually treat that input image actually we treat the input pixel as some sort of feature, but now we actually extend it in a way that we actually take the one. I think that. So before actually given this image, we want to know whether this image the image contains the cat or not. We want to compute the probability of having that the label, right? Before actually we take the actually given x, we actually compute the theta in a way that predicting whether the image contains the cat or not, right? But before actually we just use the input image x directly as a feature. But how about doing that process again even for the extracting the feature? So here, let me explain it here. Given this x, we also introduce another parameter, in this case w. You can treat that this another type. In the end, I take this sigma here, just logistic regression here. Actually, I didn't really talk about here. Actually, this actually sigmoid function that had this shape. So we just apply the same approach for extracting the feature from the x. So here, given the input x, we do the same sigmoid. We apply the sigmoid function. Then we got something, right? We got something, and then we can say that this could be actually the feature. So given the sum of the parameter, actually the different parameters, we can actually have a different actual feature point. It starts with x with a different parameter. It actually having the sum of the different features, and then starting from there, we will take another sigmoid function, and then we can do the classification. in a way, the logistic regression actually here we did actually classification. Basically, it's binary case here, whether we only compute the probability having such that actually the image contain of the cat or not. The the sure probability or not zero probability, right? Given that one, we use this one, but we also apply this one to extract the feature here. And then also this is actually the extension. We actually using the logistic regression twice, and then we can also in the end there are two unknown parameters, right? Theta and W. We can do we can adopt the same approach here. Actually, this also this the loss function even at that case exactly same to the prior the loss function of the logistic regression, but here we introduce another parameter here, two unknowns actually, and this actually the visualization of this one. Starting from x, we take the sigmoid function with a new parameter, and then it might have certain output. Let's say this h, and this we can treat that this could be the feature actually. This is our interpretation. You may we just treat this actual feature, and then we take the sigmoid, and in this case we classify. So you can treat that this actually extracting feature component and this classification. In this way, in a way, we combine the extracting feature with this classification together within one framework. Another visualization here, we're starting from x, and then for this one, you can treat that this actual neuron. It looks so you can actually that's why actually they has the name of the neural network, since actually they treat that this kind of neuron, and one neuron actually trigger some signal to the other neuron, and then we can actually have certain understanding, right? So actually that's why it has the name of neural network. You can treat that this actually this circle as neuron, and this one actually basic information that flow from the bottom to the upward, right? Basically in this case, x1, x2 might be the row level, the image intensity, and then for this one, given the for this actually h1 neuron, it gets the actual information from the x1, x2, and so on, and then with a certain this weight, right? For this neuron, we got we actually used a different weight from this different input RGB value, and then actually we actually extract certain feature, and then we do the classification, and then hopefully the classification match with our ground truth label, in this case y. And here in this level we used another unknown of theta. That's the actual parameter. Basically, in a way, this model is kind of sigmoid neural net actually. And why just using just two layer, one layer, two layer? Why not actually using the three layer, right? We're starting from the x. We actually had this layer, another layer, and also this f function, this classification. Ideally, actually, we said before, there could be the representation feature that corresponding to the very low level, like the edgy. Also, there could be the feature corresponding to the more higher level semantics, like detecting the eye, something like that, right? So we actually stacking these different layers, starting from RGB, low level layer, low level feature, and the layer corresponding to maybe the more higher level of representation, right? And then we do classification, something like that. This is actually the mathematical formulation. Okay. Overall, here in terms of optimization, actually this is actually given this RG value and weight, we get the certain loss function, right? That we talked about before with the logistic loss function that are related to that extended the classical logistic regression function, the loss, and then there might be some of the mismatch between our prediction, also the ground truth, right? And then ideally, what we did for the logistic regression is that given this loss function, we reduce theta in a way to reduce down this loss function, right? So that in other words, we match correctly with this ground truth, right? So in a way, that is a kind of back-propagate. When the information here, for the prediction, we actually information actually flow from here to there, right? It's kind of forward actually the process, right? But once we got actually the loss function, then we need to back propagate that error to adjust the weight, right? So that's why that is actually the back propagation to adjusting and computing this the weight value to reduce actually this loss function. So here it looks like the logistic regression loss function, but difference is that there are one more actual parameter, inertia to theta and W, something like that, right? And then overall we need to adjust x theta and W, so that's why we need to have two different gradients. The gradient of this loss function along the theta, so that such that we can adjust the theta in a way that to reduce the loss function. Also another gradient along the W, so that actually we can also adjust W in a way to reduce down the loss function along that line. So that could be done. That's actually once we have this one, we can adopt the stochastic gradient descent to optimize this and theta and W to reduce down the loss function. But also we can actually apply the kind of chain rule. So you can see that actually this function actually we can in a way we define that this one with the multiple variable in this way, right? So actually we can apply the chain rule and then we can derive actually the gradients by utilizing chain rule. But I'm not going to talk about those low-level details. But that could be done. Computing the gradient along the theta and W, and that's known as this actually back propagation. If you're unclear about this one, you can actually search for this very detailed information about this process. But overall, our main idea is that we can compute the gradient. Based on this gradient, we can minimize this loss function along these two different parameters. That's the high-level message. And this is a summary training procedure. We collect the label training data since it's a supervised learning. And then given this training set, we actually collect some of the training data. And then given the batch, we actually compute the gradient along the theta and W. And we update the theta and W along based on this negative gradient with this different actually learning rate, something like that. We keep doing that until we actually those actually loss function convert, something like that. So this approach actually looks very simple. Historically, this does not work. I mean, this has not worked very easily, right? But there has been a lot of issues like this. Originally, this logistic regression, the Beijing one actually turned out to be convex form, but as we had actually the multiple layers, and this one the loss function is not convex at all. So it means there could be many local minima and a lot of issues. Also, optimization is very difficult. You can compute the gradient, but sometimes gradient is very small. It's known as actually vanishing gradient. There should be gradient, right? So based on that gradient, we can adjust some of parameter. But gradient becomes 0. We don't know in what direction we have to update those parameters. Also, still it's a big issue. It's very difficult to, as you actually have your multiple layers, it's very difficult to debug. I mean, if you have some error, we have to look at it, right? You need to localize the problematic component, but it looks very complicated. All those issues, but there are a lot of things that have been improved. I'm not going to talk about most of them, but they're based on a lot of theoretical advances of engineering effort. Actually, we are now getting the very good result, even using this deep neural net. So based on that success of deep neural net, we are actually using those features technique to our image search task. One example is the nonlinearity. So if I talked about the sigmoid function, but there could be many other actually shapes. But it turns out that the sigmoid function is a little bit difficult to be optimized, but some of the recent ones use the rectified linear unit. So for example, one of the examples is that if I use this kind of shape, sigmoid shape, so suppose actually at the case we have exact actually the prediction, right? There's no code. If we actually a bit away from that exact probability of the being 1, then we should have the gradient, right? But gradient very small, right? So at that case, gradient is very small, and then if we back propagate through the multiple layer, the gradient becomes 0. So the gradient becomes vanished, so that we cannot adjust the weight. But for example, if you're using the rectified unit, if there's smaller gap, then there should be some gradient, right? Gradient should be much bigger than the prior one, right? So then we can have also we can get a sum of gradient, and then we can backpropagate, and then we can adjust the weight across the different multiple layers. So it turns out it's actually better. So I'm not going to talk about all the lot of details. There has been a lot of issues to make the deep learning technique work quite well. I'm just showing one of the examples here. So far I talked about actually the supervised deep learning. Some of I didn't mean supervised deep learning very wide, very deep field, but here I mainly talk about the logistic regression that classify the binary decision, whether it has kept the label of the 1 over the 0. And based on that, actually, we can actually stack the logistic regression multiple times in a way that we can actually extract their features. Also, we can combine them in this classifier. So, for example, I didn't really talk about here. We can treat that these are actual feature, right? We can treat that this another feature, another feature. This weight could be treated as the feature, right? And then basically, we can also use this kind of feature for the image search and something like that. I will get back to the issue later on. There's a lot of issues like optimization or initialization. So initially, I didn't really talk about initialization of the weight, but typically we need to think about what are the good starting weight for those weights, right? So also the architecture actually matters. There has been a lot of improvement of the design this network architecture. I didn't really talk about those one, but if you're interested, you can actually look at this one. But I only give you the high level the one. We can actually joint optimize of the extracting feature and also the learning classification, and then we can treat this weight of the deep neural net. We can use for the image search. There actually has been a lot of resource. For example, the deep learning. Also, there are actually deep learning course even given by the very well-known research in the deep learning, Yan Li-kun. You can also if you want to know more about deep learning, you can actually go over this one. There could be many related tutorial, also materials. Some other ones actually. Do you have question, comment up to here?
In deep learning, there are many layers, but in hardware environment, I think that there are many limitations. So, what is the best practice to adopt the deep learning architecture?
You mean the architecture?
In the research problem.
Search problem. Actually, that's a very good point. I didn't really talk about that actual details here. But later on, for example, one of simple approach is that actually here we talked about this loss function, right? But this loss function mainly for the classification, right? Whether it contains the cat or not. But the image search case actually we wanted to identify similar image, right? Basically we want to basically intuitively the similar images should be ranked in a higher the position in a short list, right? So actually, as a result of the image search, we return the 100 image as a short list, right? So most similar ones should be ranked high in the short list, right? Mm-hmm. But this loss function didn't really adopt that idea, right? So we can think about it. What are the loss function to doing that? Also, we can think about it. What are the architecture that also to accommodate the kind of the task of our this image search. We'll get back that issue later on. I will talk about them. Okay, so thanks so much to the material, and then I wish that you can understand some of the main components of deep learning. I talked about the logical regression with its loss function. I stack those ones by multiple layers and optimize it with the stochastic gradient descent, and we can use the weight of the certain layer as a feature. And then we can, at a higher level, we can use this feature for the image search. And this the same homeworks. Go over there. Before looking at watching this YouTube video, I recommend you to go over the lecture material. That way you can actually you can be more familiar with the topic. Try to come up with the one question what we talked about today. Don't worry about score, but I would just encourage you to come up with the coming up with the questions. But at least you need to write down in submit three times for the you need to submit questions 3 times before the midterm exam. And common questions that compare at the Q&A. If you want to know the answer, just let me know. Yeah, that's it. Thank you. Bye.